Welcome to this tutorial. Today I want to go through an exercise in building a statistical model, compare few variants of this model, and along the way describe various challenges and solutions. This tutorial is part of a long series based on a book by Dr. Bishop and also forms a basis for the advanced approaches to model that this book teaches us. We start with a simple synthetic data set, which is a sine function generated using values between 0 and 1. Here, x-axis represents our input variable and y-axis the output variable. As such, we use the word independent variable instead of an input variable and target variable for the output variable. The symbol used for the target or output variable will be t instead of y. Here is the Python code that I used to generate this data. As you can see that I have generated lots of data points and therefore the plotted function looks very smooth. That said, in real world problems, size of data set that we use for modeling is always a very limited subset of the population. Therefore, we will pick only 10 data points for modeling. This data set consisting of 10 points will be called the training data set. It is also true that because of a variety of reasons, the data sets used for modeling have errors. We call these errors noise. Here I have shown you that one way to simulate these errors is to add some random noise to our data set. The blue dots that you see here are the 10 sample points with noise that we will use as the data set for our exercise. So the goal here is to be able to recover the underlying function with the help of just 10 training data points that also happen to be noisy. To model one simple hypothesis we can start with is that the target variable is a simple linear function of independent variable. This is essentially an equation or model of the straight line. And we already know that it would fail for our problem. Our underlying function is not a line and for the lack of better word is quite curvy. So what if we add a quadratic term with the goal to capture the curviness of our data set? But then you should ask, why include both x and x square? Why not just x square? The reason is that when modeling we make a hypothesis that coefficients, that is W1 and W2 in this case, will adjust to accommodate both the linear and the quadratic aspects of our data set. In other words, if there is absolutely no linear aspect in the data set, then we are expecting that W1 should be a very small value resulting in the elimination of the linear part. Therefore, it is okay to include both of them. Based on the similar arguments, we can also include terms of higher order than just the square of the dependent variable. For example, we can include the cube of our independent variable as well. Therefore, a more general representation of our model could be written like this, where the symbol m indicates the maximum degree of order that we want to include. This is yet another formulation of above model, but in a more concise form. This model of ours that consists of terms of various orders is called linear model. Now the word linear implies lines to many people, and here we see independent variables with various degrees. So why are we calling it a linear model? The reason is that it is linear with respect to the weights and not the independent variables. If it still makes you uncomfortable, the way to think about it is that x square and x cube and x raised to the power m could have been represented using some other symbols. For example, instead of using x square, maybe I would have used a z, and then you would not see anything which has powers to it. More important thing is that having a linear model brings along with it many mathematical conveniences, and while maybe a tad bit away from the reality of our physical phenomena, this is the first place you want to start with. We will also talk about nonlinear models during this series. So the model is specified and the job is to determine the values of these weights, the W's. But before we do that, I want you to be aware of some different formulations of our independent and target variables that would help us in finding various solutions. For our problem of 10 samples, this model of ours would translate into 10 equations or system of equations as shown here. First thing we want to note in this formulation is that the values of the weights, that is from W0 to Wm, are same in all equations. Since these are system of equations, we can represent them using matrices as well. By doing that, we can see that the target variables form a column vector and the weights form a row vector. And all our independent variables from various equations are the elements of a matrix. In terms of symbols, we can also write above as following. I'm going to use the color blue and uppercase bold letters to indicate matrices and orange color for bold symbols with lower casing for vectors. I'm using colors, although it is not conventional, because sometimes you fail to distinguish even though the symbols are bold, and hopefully colors would help them stand out. Also, this matrix that consists of independent variables is called the design matrix. Looking at the vectors and matrices, we can easily spot the variables that we have access to from our dataset. That is both independent and target variables. And also the variables that we want to determine, that is the weights. But then how do we get these other independent variables of our design matrix, which are squares and cubes of our dependent variable, of our independent variable? You would say no big deal here, just construct them, but I want to show you a simple method to do so. Using a built-in class in scikit-learn called polynomial features. You can specify to this class up to which degree you want your design matrix. Here is a simple example of execution of this function. By the way, note that there is another terminology now for the independent variables. We are calling them now features. This is the preferred term in modern machine learning. So I might use the word features and independent variables interchangeably. Now that we have a model and its matrix formulation, we can start to discuss how to find these weights. And the first step in this direction is to formulate a criteria that should tell us how far away are we from the true values, or what is the difference between the values of target variables predicted by our model and the one we have available from our dataset. One simple criteria would be then to simply just see the difference between the values given to us by our model and the ground truth target variable. Or even better, to have a single number that represents the sum of the errors of all the data points. Now, one issue with this formulation is that we are interested in an absolute error for the data points. What if few data points result in a negative error? This could have an impact on our total error because some of the error points, some of the data points will give a negative value while others will give a positive value, and they may cancel each other, giving us an invalid value of the total error. So the remedy for that is to square the difference. This way all the differences will be positive. Now, why square and not take an absolute value? Because taking an absolute would have also made the errors positive. I'm giving you two reasons that should help you make peace with it for now. A better reason will be revealed in part 2 of this series. The first reason is that squaring emphasizes larger differences. It makes them more prominent and stand out. Sometimes it's dangerous, by the way, but quite often very useful. And the second reason is that because a square function makes our derivative calculus easier to do. And we can call this formulation of ours an error function. And this specific form of error function is called sum squared error function. But note that there is an extra item in this function now that was not there before. This is a scaling factor of half. Essentially, after plugging the scaling constant of half, when we will do calculus, it would go away because the differentiation of something quadratic looks like this. So if I take a scaling factor of half, it would cancel the 2 that you will get after the differentiation. But why all this talk of derivative calculus in the first place? Reason for that is because we want to find the values of W that gives the lowest possible values of the total error. In calculus speak, it amounts to finding a stationary point or a minima, ideally a global minima, and essentially it entails taking a derivative or a gradient of the function, and then we equate it to 0 and finally solve that equation. Here I am going to show you the steps of taking the gradient. I am representing our model function as y here. You can see that the constant half and 2 have already cancelled each other. Now I am expanding the y as the sum of the weights and the independent variable. Look at the one which is moving, the term that moved. Now I have replaced the derivative of y with respect to w as x to the power I. Reason I am able to do so is because of following. Essentially, when we are taking a derivative with respect to w, x is being treated as a constant in our model function. And therefore, the result is generalized as x raised to the power I, where I indicates the power or the order. Now, simply moving the sum of x inside. Here is one more simplification step to isolate them. And finally, we combine the powers of x in the first term. This is yet another way to write the equation where I have now used the matrix representation with the symbols A and T. This, by the way, is also the solution to the exercise 1.1 in the book, where the author asks us to show that the weights can be obtained by solving the system of linear equations. You can see that we have the same answer and the conclusion. Now we try to formulate all these terms in the form of matrix vector products. You can see that the second term can be written as the transpose of X matrix and the target vector. Again, orange is for the vector and blue is for the matrix. And similarly for the first term, it can be written as this. And finally, we would try to solve this equation consisting of matrices and vectors. Moving the second term to the right hand side, and finally we have a solution for the weights that look like this. And here it is in all its glory. Here is how you would implement this in Python using NumPy. You can see that there is one-to-one correspondence between the mathematics and the implementation here. Remember, X is also called features. So that's why the A is features.t, which is features transpose of the features, getting matrix multiplied with features. I'm using numpy.linearalgebra.solve and it would take care of inverting the matrix A. And we can also write a small function to implement the prediction as well. With all this math done, let's see the results. Here, instead of one model, we will build 4 models and they would differ from each other based on the degree of the polynomial. So here is the first one where the degree is 0, meaning that model is just a constant, and this is what the plot is showing. The second one is a model of line because the degree is 1, and as I mentioned earlier, when we had started to build the model, a line is not going to capture the underlying function. The third model is of degree 3, that is, it has not only the independent variable x and its quadratic form, but also its cubic form. Let's see how it fared. It looks interesting, it looks quite good. And the final model is using the polynomial of degree 9. This should even do better. You see, it created a curve that goes through all our training points. Interesting. Ignoring the first two models, which are completely useless, we could even have guessed it without any modeling exercise, but I included them as this is what you see in the book as an experiment setup. So the real contenders here are the models with degree 3 and 9. I'm going to call them M3 and M9. And the question here is that which model should we select? Now, I can give you a few reasons why a polynomial model of degree 9 is good, because it created a function that passes through all our 10 data points. But on the other hand, the function that it has created, the blue curve going through these points, does not look anything like our underlying true function, that is the sine curve. On the other side, even though the polynomial of degree 3 failed to capture some of the training points, the final curve does look like a sine function, if you squint your eyes a little bit. We have a dilemma here. Which one is a better choice here? Which one should I select? A better question to ask would be if there are some other criteria that we could make use of to make this decision. First and foremost, looking at just the plot to make a decision would not work if you have a multivariate data set. In other words, here we were able to plot the data because there is only one independent and one target variable. In real world, you will have a multi-dimensional data set and visualization will not be able to help. Well, you still need visualization, but not necessarily that of your data points to figure if there is a proper fit of your model or not. And the second reason, actually the more important reason, is that so far we have obtained predictions on the same 10 data points that we use to find the solution for the weights. The goal of modeling, or the ultimate goal of modeling, is so that when we see new input data or independent data, we should be able to make predictions of the target variable. So we need to run this same process again, but by using new data points that these models have not seen. Such data points are called test data set. But this still does not answer how we will select. Remember this guy, our error function? Maybe this could be the criteria. Whichever model gives us the lower value for the test data points could be a better model. But we make few mods for it. First, we multiply it by 2. Remember that we had added a factor of half to make the calculus happy, and since here we are not doing any differentiation or derivation, we multiply it by 2 to get rid of the half. Hopefully you can see that. The next mod we make is to take an average. This way we can even do a comparison across different test data sets of various sizes. And finally, since this was all squared error, we take a square root to bring it back to the same scale as that of our target variable. This evaluation criteria or a function is called root mean squared, or RMS for short. Now here is a plot showing how polynomials of various degrees fared when they were subjected to this root mean square error. On the x-axis are shown the polynomial degrees. As you can see, this time I have included many other models, essentially every one between 0 to 9. The process was done for training data points as well. So let's first see how the models fared on those. This plot agrees with what we had seen earlier. The polynomial with degree 9 has the least error or the lowest RMSE. And now is the moment of truth. What? The test error is more for polynomial degree beyond 6, or even, I would say, even degree 5 seems to have a more test error. What just happened here? It doesn't make sense. A polynomial of degree 9 is supposed to be more powerful. It has more weights. And it even did best on the training data. So what went wrong here? So here are our original contenders one more time, M3 and M9. Based on what we have seen using root mean squared error, we will have to select model with degree 3 and brand the model with 9 as the one that overfitted. Overfitting means that M9 ended up creating weights that managed to get the values that satisfied the training points. Well, satisfied really well, but it would not generalize to the new data. Once more, if you're thinking that it was apparent from the modeled curve, from the visualization, it may not be too wise to take that as a criteria. Remember that you cannot always plot, especially the high dimensional data sets. But you know what? There is still something very unsatisfying here. Theoretically, a model of degree 9 is supposed to do better than a model with degree 3. I don't want to give the trophy to M3. We can't just leave it here without doing some investigative work, and more importantly, without finding some solutions for M9 to work better for the test data points as well. So our detective work starts by looking at the weights of various models. These are the weights of various models that we built. Fortunately, we have a luxury here to look at them, as we only have, 10 of them. In modern machine learning, you will have millions of parameters. This inspection will help us get some insights into what happened. If you look at the weights of M9, notice that they are very large values in both directions on the number line. There are big negative numbers and big positive numbers. And as I mentioned earlier, maybe in order to satisfy the training data points, the model with degree 9 most likely ended up adjusting these weights in such a way that it worked out. It worked out really well. So what could be the remedy here? Let's throw some ideas here. Well, since the weights got adjusted to satisfy the data points, maybe if we have more data points, then the adjustment should respect that. And maybe having a large number of training data sets should also be reflective of what we might see as test data points. More training data you have, more patterns you are showing it to your model. So I tried that, and here are the results. The results are only shown for M9. I increased the data points for fitting to 15 and 100 as well. And even the 15 seems to perform better. See here that even for 15, the curve is now somewhat sine curve like. And for n equals to 100, it is definitely a sine curve. Let me remove the training data point so that you can see it for yourself. And it also did good on test data set as well. So you see here, by increasing the size of our training data set, we managed to remove the problem of overfitting. And it is fine. But we must also acknowledge that we do not always have access to large data sets. There are data sets that takes long time, decades to collect, and consist of only few data points. And it just doesn't make sense to sacrifice a more capable model because it might overfit. So for a minute, ignoring the possibility of increasing the data set, we need to look at one more remedy to fight this evil of overfitting. And for that, I bring back our error function. One technique that is used to control the weights to obtain large values is to regularize them. Regularization here is done by adding this additional term to the loss function. The lambda here controls the amount of the regularization you want to add and is a hyperparameter here. That is, you need to figure it out by experiment what value of lambda works better, or in our case gives the lowest root mean squared error on test data. We then apply the same process of finding the minima of this modified error function, and this leads to the solution of weights that look like this. I'm not showing you the derivation step here, but it would come out to be like this. Now you can spot, if you remember the solution that we had in the case of one without the regularization, the only difference here is that there is this additional term that has appeared. This mechanism or trick is known by various names. It is called regularization. It is called shrinkage in statistics, as you are reducing the values of the weights, and it is called weight decay in modern machine learning. Even though there are many terms to describe the same mechanism, at least I would say all of them express the same sentiment. This modified form of regression is called ridge regression. Here I am going to show you the plots when I applied the 3 different values of lambda to the model with degree 9. The experiment in the book uses log lambda, but really when implementing in Python, you just use the values of lambda and not log of it. You would be able to see it in the notebook where I have all the source code. The first is an example where the value of the lambda is 0, which essentially amounts to no regularization, and you can see that there is no change in the model function. It is still touching all the training data points, but the final curve does not look anything like sine curve. So nothing new here. There is no regularization because lambda is 0. The other extreme example is when the value of lambda is 1. In this case, the model fails miserably. We can say that this is too much regularization. And in the final case, we use a very small value of lambda and the curve shows up quite nice. It almost looks like a sine curve now. So again, please note this is for model 9. Let's look at the weights as well to see the impact of regularization. You can see that for lambda equals to 0, these are the same values that we had when there was no regularization. Well, lambda equals to 0 means no regularization. These are very large negative and positive values that have managed to work really well for the training data set but failed on test. In the case of extreme regularization, we can see that the weights are significantly reduced, almost to 0. Look at this, 0.03, 0.07, 0.09. Essentially, this is the reason why the lambda equals to 1 crashed our model. It did not learn anything. And finally, the winner here is log lambda equals minus 18, which gives us just the right values of weights. You can see that they are not very big numbers, at least not as big as the one that we are getting when lambda equals to 0. So this is the final check. With the help of root mean squared value and the test data, we can see that the train and test errors are now not very different anymore. If you recall in the previous case, the test errors and the training errors were significantly different for polynomial of degree 9. So this trick of regularization or shrinkage made M9 work well on test data points as well. But you know what? There is something still quite unsatisfying with all this formulation. How the heck adding this term worked? You may think, why care? It was proven it worked. Proof is in the pudding, as they say. But I'm not happy. As such, even though I did give you mathematical justification behind the sum squared error function, why we are squaring it, why we are multiplying by half to make calculus happy and whatnot, it still felt like I justified the formulation after someone forced me. As if someone gave me this error function and said find reasons to believe that it works, And in many ways, this is what I did here. I'm not even talking about this additional regularization term. For this one so far, I have not provided a good justification. Yes, the solution worked, but that's not a way to develop an intuition. Just because something worked does not necessarily mean that we understand why it worked. And the reason for this struggle here is because this view of curve fitting is very limiting. We ought to have a perspective, a view, an explanation that makes all this formulation of error function, including the regularization term, emerge naturally. And that would be the topic for the next tutorial, and maybe next tutorial after that, and many other tutorials in this series, where we will arrive at all this from a very different starting point. And I'm confident that it will help you become more comfortable with all this formulation, as it surely did for me. And with this, I end the tutorial for today and the part 1 of this series. I would like to thank you very much for the time you gave here. I hope this tutorial was helpful. I'm hoping that even though you may have known linear regression, this helped you see some other aspects to it and hopefully raised some more questions for you. Let me know in comments your feedback, if any. Bye bye. See you next time.